Welcome to Extraordinary Concepts in Physics. This is the second of the potpourri, the mixed bag of things that I couldn't fit in elsewhere, so there are little bits here and there, mostly involving quantum mechanics, but not only. There's a bunch of these, so let's get to them. I'm Robert Nemiroff. This is Michigan Tech, and you can find these things, all of these lectures online here, and it's on iTunes too. Please look at them all. I focus on concepts. I'm not really interested in so much math, although there will be a little bit of math here. So, one thing I did mention briefly, it's very powerful, was actually developed in Einstein's time by Emmy Noether. It's called Noether's theorem, which is really powerful, and it's used a lot in physics today. When Einstein saw this, he thought this was very clever. He might have wondered why he didn't come up with it himself. So it's the idea that symmetries underlie conservation laws. And that assumes principle of least action. So for instance, if you have a symmetry that is rotation, then you will have a conservation of angular momentum. If you have a symmetry that involves translation, you will have conservation of linear momentum. And if you can identify a symmetry that involves time, you will have conservation of energy. Now, these are not the only ones that there are. There are more, and many of them are used in higher level quantum mechanics. But it's a very powerful theorem. It's a very powerful way of thinking about things. It's very clever. Noether's theorem. Okay, acceleration, jerk, and snap, the movement paradox, as I like to call it. So to move from rest, an object must have to change its position. So over time, so that means it must attain a velocity v, right? So that's for nothing controversial. To attain velocity v from rest, though, one must accelerate. So you must gain some acceleration a. But how does an object attain acceleration from rest? And then how does it do the next one? Oops, always happens. There are infinite numbers of terms of motion, higher derivatives of motion. The next one after acceleration is jerk, and the next one after that one is snap, which sometimes is called jounce. How come you don't hear about these in introductory physics? How come you don't hear about these in everyday life? How come your car doesn't have a snap-ometer instead of accelerometer? Or something that tells, well, because you can usually get away with explaining things with just position, velocity, and acceleration. So it's sort of a secret, I don't know, it's sort of just the way we've done things, and it makes it much more complicated, and it's much harder to solve the higher differential equations that are implicitly involved in jerk and snap. But that doesn't mean they don't exist. In fact, if you're going to move any object that it's at rest for some period of time, then you're going to have all of these terms. You're going to have an infinite number of terms that all change. And that is what I call the movement paradox. It's hard to think that movement exists because something at rest to move must have its infinite order derivative with respect to time change. Okay, I promised this in another lecture. So this is charge versus mass. Everybody likes to think that they're the same, only different. But actually, you can think about things that are speed invariant in physics and things that change relativistically in physics. So one thing is speed invariant is charge. So if you take charge and you accelerate it to high speeds, you still have the same amount of charge. However, if you take mass and accelerate it to high speeds, moving relativistically, it's going to appear to have much more mass. So they're not exactly the same. Electricity and gravity have fundamental differences. Also, something that has fundamental spin. A charged particle isn't going to change its spin. An electron doesn't have more spin when moving quickly. However, it might have more energy. Magnetic moment is the same, and wavelength is the same. So there are things that line up on either sides of these, and charge is not the same as mass. Jumping around again. I can get this thing to work. Oh, great. Okay. Well, I like to think of this as experimental relativity. It's something I sort of come up with. So E equals mc squared, probably the most famous equation in physics. Come up with Einstein, really great. However, that's a theorist's point of view. And from an experimental point of view, why don't we break it down? What do we know really is a multiplier there? Is it 1? Is it exactly 1? Maybe it's 1.000001. Maybe it's not exactly mc squared. Maybe m is not exactly to the first power. Maybe it's 0.999998 power. How do we know that? How do we know there's not a 0-point term, like dark energy? How do we know that c is exactly squared? All of these can be considered variables that can be constrained by experiment. So we don't really know that E equals mc squared. What we do know is that boundaries on alpha, beta, gamma, and zeta, are all within some different tolerances. And many times physics is interested in putting better tolerances on those. And who knows, maybe one day we'll find out it's not exact. Not exact. Okay, this is something I thought of. So I collect things that I've thought of over my life. So when I was even in high school, I would notice that, strange as I am, if I was to look at a different light source over the bridge of my nose, I could see diffraction pattern, which means that since I'm not using any modern technology, diffraction was probably visible for as long as humans could think. For as long as humans had eyes and noses, there was something that was not understood that could be now understood in quantum phenomena as diffraction. And then I realized later, oh, you can try this, just look at a distant light source, that it's even simpler than that. You don't even need your nose. It's more plain than nose on your phone. Quantum effects can be seen just by having an imperfect vision, which everybody has, and something, a little bit dirt or something on your lens, an imperfect lens in some way. You can take your glasses off if you wear glasses, and look at a dim, distant source. And you will notice that there's not just one source that appears to be there. Sometimes you have to train your eyes to do this. You will notice there's lots of things. Those are called speckles, and we see them due to the Earth's atmosphere. Not only that, but if you keep thinking about those speckles and you keep looking at them, you'll notice those speckles have rings around them. Those are diffraction rings. So quantum mechanical effects are plainer than the nose on your face. You can see them just with your eye. P versus NP problems. I've read about this recently. This is technically a computer science problem, but I have a feeling it's going to merge into physics, or somehow physics will become involved in this at some point. In particular, the question P versus NP asks is, can answers be generated as quickly as they can be verified? In particular, if answers can be verified in polynomial time on a computer, can answers be generated in polynomial time as well? So the intuition I have as a physicist, which is irrelevant, nobody cares what my tuition is that no, that one can open a lock quickly given a key, but one can't generate a key as quickly. However, this seems to me that if you were to take physical analogies to this, it could be related to the arrow of time, because you can go quickly in one direction but not in the next in solving a problem, and it might be somehow related to wave function collapse or decoherence. And with that, unfortunately, I'll jump to something else because I have to jump around quickly here. So the holographic principle is something that gets a lot of play today. Difficult to describe in one slide, but here we go. So conjecture has it that a volume of a space has all its information encoded on the area that bounds it. So let's say you have a sphere here, and you can tell because it has a little window there. So this is a sphere. So all the information in that sphere, according to the holographic principle, is encoded on the boundary of the sphere. And one of the trains of logic that led to this is black holes. Things that fall through black holes have to fall through the event horizon. Possibly they leave some kind of, all you need to know is about the event horizon of a black hole and you can know everything that's in it. So a lot of string theories, which we'll get to in another lecture, a lot of string theory conjectures have a lot to do with the holographic principle, and there's some thinking that it might be applicable to cosmology. The Unruh effect. So this is strange but true. So accelerating observers measure different black body radiation than non-accelerating observers. So typically with relativity you deal with observers moving at a constant velocity and or some velocity. To get into acceleration gets you sometimes into general relativity, although acceleration is dealt with in special relativity alone. However, what Unruh found is that if you move stuff about, things change more fundamentally. So for instance, let's say you had a thermometer, and you would just hold this thermometer at rest, and it would read 0 temperature, say, no radiation around. Now you wave this thing about. Here, I'll show the wavy line. So you wave the thermometer about. Then you're suddenly going to get the thermometer reading a temperature, even if there's no radiation. Well, I won't say that. I'll just leave it at that. It will read a finite temperature if you wave it about. So you can actually calculate how hot it would get, and there's not a lot of, compared to stuff we would see in your normal everyday life, there's not a lot of temperature reading on that thermometer measured in 10 to the minus 21 kelvins meters per second squared, where here A is Planck's constant reduced as acceleration, Boltzmann constant, but it's really strange that it happens, and it's somehow fundamental. The Higgs mechanism. Things looking for this like the Large Hadron Collider. It is known that masses exist. It is known that masses have gravitational mass. It is known that masses have inertial mass. So the question in particle physics is, why does mass have inertial mass? What creates momentum, for instance? So one leading mechanism for this is called the Higgs mechanism. So in this view of the universe, space is filled with a virtual sea of Higgs bosons, among other things. It's filled with lots of stuff. Fundamental particles perturb this sea so that a crowd of virtual Higgs particles surround it. Slogging through this field creates inertial mass. That's the idea of the Higgs mechanism. So for protons and neutrons, inertial mass is thought to be mostly provided by the exchange of virtual color gluons. Okay, strangelets. So we're going to get to a very strange note with strangelets. They're a form of matter not seen on Earth, we don't think, consisting of equal numbers of up, down, and strange quarks. Strange nucleons don't contain strange quarks. Strangelets, though, are more compact than normal matter. They may grow to arbitrary size, and they may involve runaway reactions that might make regular stars into strange stars. It could be that if anything that touches a strange nucleon itself turns into strangelets, into strange stuff. Therefore, the universe, if a strangelet was to strike the Earth, it could make the Earth completely into a hot, smoldering mass of strangelet matter. It could destroy us all, so far as we know. Okay, I'll go through the Large Hadron Collider, which is the biggest, so this is being taught in the fall of 2010. So the Large Hadron Collider has been on for a little bit, but it's still ramping up in power. It started in 2009, has some good stuff, hasn't yet discovered limits, hasn't discovered Higgs boson. So its purpose of the collider is to rule out predicted Higgs boson or find it, bolster the Higgs mechanism, find supersymmetric partners. This is in particle physics. Extraspatial dimensions might be found or excluded. Dark matter particles might be found or excluded. So there's a lot of interesting parameter space that it's going to look through and find stuff or exclude stuff. So people are looking through this. If you're seeing this lecture in the future, it might have done that already. There are some controversies which either they'll have happened and there'll be a short period of chaos on Earth after which the Earth is destroyed, or they didn't happen, in which case you're watching this at home more relaxed. So there's some people who are worried that the Large Hadron Collider would create micro black holes that would devour the Earth. So if you want to read about something, science fiction about this, there's something called the Crone experiment, which is really cool about somebody who, science fiction, created a black hole in the lab in high pressure density situations, and it fell out of the lab, and Earth had a problem because this little thing was falling back and forth through the Earth. So people are worried that the LHC, Large Hadron Collider, will also create micro black holes, but people also argue that this is unlikely to happen. It hasn't happened before. There's cosmic rays that come streaming through the universe at extremely high energies that are continually impacting on the Earth, and they haven't created any. So we're not expecting this to happen. Strangelet controversy with regard to the Large Hadron Collider, again, is that maybe that the LHC would create strangelets, and then it would just have to start bumping into things, and those things would bump into things, and those things would bump into things, liberating energy, and soon the Earth would again be a smoldering mass of strangeness. Again, if it happened, let me apologize before it happens. We're sorry, we didn't know it would happen, but no one's going to be here to hear that, so it'll be a pretty quick done deal. However, if it didn't happen, you shouldn't have worried about it. Again, there's indications from cosmic rays that we don't have much to worry about. Strangelets were more likely to have been created in other colliders, but they've never been found. So these are potential doomsday scenarios that are fun to think about, but I think the Large Hadron Collider is going to be remembered for finding really cool stuff or excluding things that we thought were there, and so helping us to rethink the world around us. And with that, I will conclude this lecture on Potpurri quantum mechanics and ask you to keep Schrodinger away from your cat. Thanks. Bye. He might have wondered why he didn't come up with it himself. So it's the idea that symmetries underlie conservation laws. And that assumes principle of least action. So for instance, if you have a symmetry that is rotation, then you will have a conservation of angular momentum. If you have a symmetry that involves translation, fit in elsewhere, so there are little bits here and there, mostly involving quantum mechanics, but not only. There's a bunch of these, so let's get to them. I'm Robert Nemiroff. This is Michigan Tech, and you can find these things, all of these lectures online here, and it's on iTunes too. Please look at them all. I focus on you will have conservation of linear momentum. And if you can identify a symmetry that involves time, you will have conservation of energy. Now, these are not the only ones that there are. There are more, and many of them are used in higher level quantum mechanics. But it's a very powerful theorem. It's a very powerful way of Welcome to Extraordinary Concepts in Physics. This is the second of the potpurri, the mixed bag of things that I couldn't concepts. I'm not really interested in so much math, although there will be a little bit of math here. So one thing I did mention briefly, it's very powerful, was actually developed in Einstein's time by Emmy Noether. It's called Noether's theorem, which is really powerful and it's used a lot in physics today. When Einstein saw this, he thought this was very clever.